Hi, good morning all. So in this class we will discuss about the MOSFET amplifiers. So let first getting into the circuit diagram for MOSFET amplifiers, we'll see the construction of the MOSFET amplifiers. So here we have the P-type substrate, and two N plus doped regions. N plus means heavily doped. Okay, so two heavily doped N plus regions from which the contacts are made for the source and drain, and since it is a MOSFET, okay, the oxide layer is formed above this P-type substrate, and over that metal layer is formed, and that the terminal is called the gate. So only it is called the metal oxide semiconductor FET. So two layers of metal and oxides are there over the substrate. Okay, so it is called the metal oxide semiconductor FET. From that the gate terminal is taken. So this is the structure of the MOSFET. Okay, so this is the N channel MOSFET, source, drain, gate, substrate is there. So electrons are induced in the channel. So this is called the depletion region. So this is called the depletion region. L in this diagram, L is the this is the channel. The distance between the two N plus regions is called the channel. And say L is the length of the channel, and W is the width of the channel. So here W is not marked. So L is the length of the channel. Okay. This is the depletion region where there are no charge carriers. And okay. So three terminals are there: source, drain, and gate. Substrate is covered the body, which is the fourth terminal. Substrate is P-type doped. Okay. Electrons is induced in the channel when a positive voltage is applied to the gate. So electrons are induced. Electrons moves from source to drain. Electrons will move. The flow of electrons will from source to drain. So the current flow will be in the reverse direction from drain to source. So creating a channel for current flow. So we have to create a channel for the current flow. So metal oxide semiconductor is a capacitor. So this MO, that is metal layer and oxide layer, acts actually as a capacitor. Okay, MOS is a capacitor across an insulator. Okay, when a positive voltage is applied to a gate, the electrons are induced under the gate. The electrons are induced under the gate. At threshold, sufficient number of electrons form a channel between the source and the drain. So this from the source and the drain, a channel is formed. So that is called the induced. It has been marked as induced N channel. A channel is marked. A channel is formed. Okay. Through this channel only the electrons flow. Okay. How a pipeline goes between 2 points, like the between 2 points, like that. Between the two source and the drain region, a channel is formed. N channel. So if it is N-type MOSFET, N channel is formed. If it is P-type, P-type channel is formed. Okay. So the total charge on the channel is given by Q equal to CQX into W into L into VGS minus VT. Okay, so this is the total charge, where Q equal to CV. So this is the formula, Q equal to C into V, where C is capacitance or formula epsilon into A by D. So epsilon 0x is the oxide capacitance, oxide capacitance. Sorry, COX is the oxide capacitance. Epsilon is usually the permittivity. Epsilon is the permittivity of the oxide layer, and TOX is the thickness of the oxide layer. A is the area, where A is given by W into L. Width into L is the area. So see, here we have epsilon A by D, epsilon 0x into epsilon OX, oxide capacitance, into A is W into L, divided by T is the thickness TOX. So this three terms form the capacitance, into CV. Volt is a voltage. VGS minus VT. VT is the threshold voltage. Okay. Gate width, gate length. VT, gate width, gate length, and VT is the threshold voltage. Okay. So this is how, this is the expression for the charge. Okay. Please understand this so that we will have a better understanding of the amplifier. Okay. So what is meant by signal? So any signal, sound signal. Suppose I am human producing a sound is a signal. Suppose if I am waving my hand, it is a signal. So that is signal. What do you mean by analog signal? One which continuously varies with time is called an analog signal. What do you mean by linear amplifier? If there is a linearity between the input and the output, it is called a linear amplifier. That means the output is directly proportional to the input signal. So that is called the linear amplifier. As previously said, small signal means that we linearize the AC equivalent circuit. Small signal means it operates in the AC region, linearized region only. It will not go to the saturation region. So it operates in the linear region. Okay. So in terms linear amplifier means you can use superposition, so that DC analysis and AC analysis of the circuit can be performed separately. For a circuit, we can perform both EC analysis and DC analysis, and total response of the circuit is the sum of the AC response and the DC response. So that is called the total response. Okay. So that is how we are defining the linear amplifiers. We can use superposition of the DC and AC analysis. For a linear amplifier, we can use superposition of DC and AC analysis. So this diagram shows the NMOS common source circuit with time varying signal source in series with gate source. Okay, common source circuit. So here the source is grounded. Source is grounded. So for MOSFET, you have to draw the symbol somewhat different. For JFET, you will be drawing a single line for gate. Here you have to draw the double line, since it another oxide layer is there, so you have to draw a double line. So one large line and one small line. Okay, so the மாதிரி symbol போட்டுக்கோங்க. And then source is grounded here at the gates. Here we are giving the input at the gate VA, both DC power supply for biasing and the AC input. So two individual DC and AC sources are given, and similarly for the drain we are given the power supply VDD. The output is taken at the drain V0. So this is the circuit diagram, and when this is the plot of the drain characteristics. So previously for JFET we refer the transfer characteristics. So this is drain characteristics, VDD versus ID. So the operating point lies in the saturation region only. So remember here this is the Q point. So this is the Q point. So this is the DC load line, and the Q point lies in the saturation region. That is, saturation region means ID remains constant if you vary the VDS. Okay, if you vary the VDS, this ID is a straight line. So the Q point always lies in the saturation region. Okay, that's what we are saying. The Q point lies in the saturation region, and this is the variation of VDS, this is the variation of ID, and this is the variation of VGS, small signal variation. That's what we have explained here. Okay, now this is the summary of the notation. So suppose AC values means, as I previously said, it will also be represented by small letters, ID, small VGS. This is AC values. DC means full capital, full ID capital, VGS capital. Instantaneous means addition of DC and AC means I is indicated in small letter, D is indicated as capital letter, V is indicated as small letter, and GS is indicated as capital letter. This is as far as total VGS. So these, please follow the notations. It should be very important. Okay. So AC means full small letter, DC means full capital letter. Instantaneous means one small letter or one capital letter. Instantaneous na total of DC and AC. Okay, please keep with this. Phasor means ID VGS. So this is how we have to represent this. Most of the time we won't be using. So please be thorough with the first three logics. Okay. So how to represent DC values, how to represent AC values, how to represent the total instantaneous values. So we see from the figure. So from this figure we are writing these equations. Keep these figures in mind, and we are writing the expression as VGS equal to, so this is AC voltage. Okay, VGSQ plus input voltage VA. So VA is VGS. Okay, and we have another expression for the drain current for FET. Okay, ID equal to Kn into VGS minus VTN the whole square, where VTN represents the threshold voltage, N indicates the N channel MOSFET. So this is the expression for ID, where Kn equal to 0.5 or 1 by 2 mu N COX into W by L. W is width and length of the channel. W is width and length of the channel. COX, as we know, oxide capacitance. Mu N is the constant. Mu N is the mobility. And Kn, okay. So this is the expression for the constant Kn. So the drain current is related by Kn into VGS minus VT and the whole square. So now you substitute in this. Substitute this 4.1. This is expression for VGS in this. So we are getting the expression like this. When we expand this, Kn into VGS minus VT and the whole square, A plus B the whole square like expand A square plus B square plus 2AB. And this term, the third term, is very small compared to the second term. So what we are trying to say is, the first term is in the equations there are three terms. First term is a DC current. So here we have the first term is a DC term. See, because we have written everything as capital, so it is DC term. And the second term is the time varying drain current component. So here we have small VGS. So we have AC component, time varying AC component. So first term is DC component, second term is AC component, and the third term is proportional to the proportional of the signal voltage, VCGS square and square of VGS. So this here there is square of VGS. So the squared term now we will produce undesirable harmonics, or which will result in distortion. Always the square, cubic or higher order harmonics will result in distortion. So to minimize the distortion, we should consider that, so VGS should be less than or equal to this term, that is VGSQ minus TVTN. So yeah, so always be careful that VGS should be less than or equal to 2 VGS minus VDN. Okay. So now ID equal to IDQ. So ID equal to, this is instantaneous current. ID stands for instantaneous current, equal to, this is DC current. IDQ is the DC current plus AC instantaneous. This is the total instantaneous, this is AC instantaneous ID. So this is the expression. So the AC component of the drain current is given by from this equation. As I said, this is the DC component, this is the AC component. So we have written the AC component along. And substitute, see GM, transconductance is the ratio of drain current to gate source voltage. So this we have previously studied, slope ID to VGS. So ID to VGS is the transconductance, which is equal to, so from this equation, ID by VGS equal to 2Kn VGSQ minus VTN. Okay. So this is the thing. Next you substitute VGS. So from this we have found GM, so bring this 2Kn below. So GM by 2Kn. And already we have the expression ID equal to Kn VGS minus VTN the whole square. From this you find, now you substitute VGS minus VTN equal GM by 2Qn. So we have GM by 2Qn the whole square. If you simplify this, you have ID equal to GM square by 4Kn. Either cross multiply, the root GM square equal to 4 ID Kn. If you take root of this, you will be getting 2 root Kn IDQ. Of course, this is the IDQ. DC, the ID bala நம்ம என்ன போட்டுருக்கோம்னா IDQ, DC bias quiescent value போட்டுருக்கோம். So we have derived the expression for transconductance. Okay. So this is all the introduction. இதனால தரவா படிச்சுக்கோங்க. And this is the superimposed sinusoidal voltages, VGS versus ID. VGS versus ID. Okay. VGS versus ID na transfer characteristics only. சரியா, VGS versus ID. Okay. Next. So the thing has been explained here, and one problem has been problem. Calculate the transconductance. What are the things we have given? VTN கொடுத்திருக்காங்க, half mu n COX கொடுத்துட்டாங்க, W by L, width, channel width to length கொடுத்துட்டாங்க, drain current கொடுத்துட்டாங்க. So directly substitute what is the transconductance கேட்டிருக்காங்க. First you find Kn, half mu n COX into W by L. Substitute பண்ணி Kn கிடைச்சிருச்சு. Then you know that GM equal to 2 root Kn IDQ. IDQ நம்ம கொடுத்துட்டாங்க. So நம்ம வந்து transconductance கண்டுபிடிச்சிட்டோம். This problem may be asked. Okay. So this we have completed the basics of MOSFET amplifier. GM எப்படி கண்டுபிடிக்கிறது அப்படிங்கறத நம்ம தெரிஞ்சுக்கிட்டோம். இதை யூஸ் பண்ணி தான் காமன் சோர்ஸ், காமன் கேட், காமன் ட்ரெயின் வந்து கன்ஸ்ட்ரக்ட் பண்ணோம். சரியா? So this is the common source amplifier. Say source is grounded, drain resistance. And common source NMOS transistor with the small signal parameters and simplified small signal equivalent circuit. Okay. This is the current source. So GM, VGS, ID. So whatever we have drawn for FET, it is equivalently applicable here also with minor differences. Okay. So here the drain current expression is as we have already written, Kn into VGS minus VTN the whole square into 1 plus lambda VDS. So the instantaneous, so here we are writing the instantaneous drain current, capital V, 1 plus lambda VDS, where lambda is a channel length modulation parameter and is a positive quantity. Channel length modulation parameter. And the small signal output resistance. Here we have to, previously we have in the JFET we have included small RD. Small signal output resistance we have included R small RD. Here we have to include small signal output resistance RO. RO is given by lambda Kn into VGS minus VTN the whole square, the whole inverse. Okay. So this is the expression for, there is ID by VDS. So here we find ID by VDS. Here we find ID by VDS. Okay. When you find ID by VDS, it will be given by lambda Kn into VGS minus VTN, because இது வந்து கீழே வந்துரும், இந்த சைடு போயிடும், ரைட் ஹேண்ட் சைடு போயிடும். So the whole inverse, which is equal to lambda IDQ the whole inverse. So இது again IDQ. So R0 equal to lambda IDQ the whole inverse. So this is the expression for output resistance. So you connect, now you connect the R0 in parallel with this current source GM/VGS, and this is a small signal equal. So R0, again you have the drain resistance RD. So this is the common source. இதுக்குரிய expressions வந்து derive பண்ணிக்கோங்க. However, we have derived for அந்த இடத்துல RD க்கு பதிலா you have